get started on that, let me start with a force diagram. So here's the ball. There are three forces acting. There's the string pulling to the right. I'll call that Ft for tension. Gravity pulls down. I'll call that F grav. And the spring is pulling up and to the left. I'll call that Fs. Since we know that the ball isn't moving, or the ball is in equilibrium, either way, that means that the net force is 0. So if I add up all of these forces, the spring force plus the tension plus gravity, those all add up to 0. So as next step, I'm going to write down each of these forces in component form. To do that, let me choose this x and y axis. So here is y, and here is x. So we're making the usual choices for the x and y axes. Then the tension is pointing in the plus x direction. I don't know its magnitude, so I'm just going to call that magnitude Ft. Gravity points in the minus y direction, and I know the formula for that is mg, so I'll write this as minus mg. The spring force, I don't know its strength, but there is this formula I can use for writing down a vector in components, that the spring force, the vector, is magnitude times cosine of theta x. I'll draw a picture showing where theta x is in a second. Fs cosine theta y, and the z component is 0. So let's talk for a moment about finding what theta x and theta y are. Let me redraw F sub s, and here is y and x. Theta x is the angle between Fs and the x-axis. Theta y is the angle between Fs and the y-axis. Now you might ask, how do we find theta x and theta y? Let me draw, to get that, let me draw a triangle. So we are told that the length of the spring is 15 centimeters and that this distance is 8 centimeters. And so with those two bits of information, I can find this angle, which is the same as theta y. I would get that from the sine function. So sine of theta y is the opposite side, 8 centimeters, over the hypotenuse, 15 centimeters. And if I put all that stuff into my calculator to calculate theta y, and then convert that to degrees, I get 32.2 degrees. Theta x is always 90 plus theta y, so in this case that's going to be 112.2 degrees. So before we turn the page, let's stop, look where we're at here. So we know that these three forces, Ft, F grav, and Fs, add up to 0. Of these, the only one that I know for sure I can calculate is mg, because I have mass and I know g is 9.8 newtons per kilogram. I have numbers for the angles theta y and theta s, and so hopefully when I combine all of this stuff together, I'll be able to calculate the two unknown forces, Ft and Fs. So let's take a look at that. So I'm going to repeat what I had on the previous page. So Ft is the magnitude Ft that we don't know, 0, 0. F grav, 0, minus mg, 0. And Fs is Fs cosine theta x, Fs cosine theta y, and on the previous page we found numbers for theta x and theta y. And I know that if I add the three of these together, I get F net. And because the ball is stationary, F net is 0. And if I add the three vectors on the right-hand side, I get Ft plus Fs cosine theta x minus mg plus Fs cosine theta y, comma 0. Oh, sorry, I just looked up at the screen. I'm not quite sure what happened there with those lines. All over the place, but so let's see. So three equations here, right? Because the x component must be 0, the y component is 0, the z component is 0. So it must be the case that Ft is minus Fs cosine theta x. And so if I can find Fs, then I can get Ft. And it must be the case that Fs cosine theta y is mg. I know mg and theta y, so let me get Fs. That is mg over cosine theta y, which is a mass of 0.45 kilograms, g is 9.8 newtons per kilogram, and the angle theta y was 32.2 degrees. And when I plug all of those numbers into my calculator, I get see, 0.45 times 9.8 divided by cosine of theta y. I get 5.2 newtons for Fs. Now that I have Fs, I can find Ft. And on the homework questions like this, you might not have to find what we're ultimately going to find here, which is the unstretched length of the spring, but the questions are going to have several forces that add up to 0. The process you're taking is to write them out in component form like we did, add them all together, set each of the components to 0, and solve for what you don't know. So we had Ft was minus Fs cosine theta x. So that's minus 5.2 newtons times cosine of 112.2 degrees. Now, quick note, that cosine of an angle bigger than 90 degrees is going to turn out to be a negative number. So what I get when I multiply all of this together will be a positive number. That makes sense. In our drawing, the Ft was to the right. So let me consult the calculator here. So minus 5.2 times cosine theta x, I get positive 2.77 newtons. So in many problems like this, you'll be done. You'll be asked to find one of the unknown forces. We've just found all of the unknown forces. We would be done. In this question, we're supposed to find, in addition to these forces, we're supposed to find the unstretched length of the spring and to do that, let's remind ourselves of another formula we have for the spring force. The magnitude of the spring force is the spring stiffness K times the stretch, and we'll think about that stretch as being the length of the spring minus the unstretched length. So here L is 0.15 meters is the stretched length. L0 is unstretched, and the one bit of information that we have from the problem is that L is bigger than L0. Okay, so where do we go here? We have a number for Fs, that's 5.2 newtons. We were given a number for Ks, so we can solve for L0. So let's see, Fs equals Ks, L minus L0. I'm dropping the absolute value because I know L is bigger than L0. Divide both sides by Ks, so L minus L0 is Fs over Ks, and so L0 must be L minus Fs over Ks, and if I plug in all of the numbers we're given, I get 0.15 meters minus 5.2 over 110 newtons per meter. I get 0.103 meters, so a little over 10 centimeters, which seems, I don't know, seems reasonable to me. There we go. Let me know if you have questions.